ECE EEE 201 Electrical Circuits 1. In this section of the lecture, we will basically discuss the basic laws and resistive circuits. That includes Ohm's law, Kirchhoff's current law, Kirchhoff's voltage law, series circuits and parallel circuits. Series circuits. In series configuration, the total resistance of resistors in series is unaffected by the order in which they are connected. That is, irrespective of how you connect R1, R2 and R3, if they are connected in series, the total resistance will be the same. There are certain steps which we need to follow to solve the circuit connected in series. Number 1. In series configuration, the same current will flow through all the elements in the circuit. We know that according to Ohm's law, V, that is voltage, is equal to IR, that is current multiplied by resistance. Since the same current will flow through all the resistors in series configuration, thus the voltage drop across R1, R2 and R3 will vary depending on their respective resistances. Number 2. The current will always enter through the negative terminal of the source and will come out of the positive terminal. Number 3. In case of a resistor, the polarity of the voltage is determined by the direction of the current. That is, unlike the source, the current will enter through the positive terminal of the load and come out of the negative terminal. Thus, we have assigned the polarity of V1, V2 and V3 as shown over here. Based on the given circuit, we have to determine the total resistance RT, the source current IS and the voltage across each resistor. As I have mentioned in the previous slide, that in a series configuration, the same current will flow through all the elements connected in series. This current will enter the source through the negative terminal and will leave the source through the positive terminal. The current will enter the load through the positive terminal and will leave the load through the negative terminal. Based on these points, we have assigned the direction of the current and the polarity of the voltages across the resistors R1, R2 and R3. The first question says that we have to find the total resistance RT. By looking at the figure, we can say that the resistors R1, R2 and R3 are connected in series. Thus, RT equals R1 plus R2 plus R3, which is equal to 8 ohm. The second question says we have to calculate the resulting source current IS. Well, we know the total resistance of the circuit, which is 8 ohm. We also know the source voltage, which is 20 volt. Thus, using Ohm's law, we can determine IS using the formula E by RT, which is equal to 2.5 ampere. The third question says that we have to determine the voltage across each resistor. Well, we know the resistances of each of these resistors. For R1, it's 2 ohm. For R2, it's 1 ohm. And for R3, it is 15 ohm. We also know the current flowing through each of these resistors, which is 2.5 ampere. Thus, we can determine V1, V2 and V3 using Ohm's law, which is I1 R1, I2 R2 and I3 R3 respectively. By substituting the values of I and R, we can determine V1 is equal to 5 volt, V2 is equal to 2.5 volt and V3 equals 12.5 volts. Example 2. In this example, the question states, given RT and I3, calculate R1 and E for the circuit in the figure. If we look at this figure, we can see that we already know the total resistance RT, which is 12 kilo ohm. We also know the value of R2, which is 4 kilo ohm, and R3, which is 6 kilo ohm. We also know the current flowing through R3, which has been marked as I3 and is equal to 6 milliampere. Now, we have to determine the value of R1 and the value of E. At first, let us determine the value of R1. We know that R1, R2 and R3 are connected in series. Therefore, RT equals R1 plus R2 plus R3. If we substitute the values of R2, R3 and RT in this equation, then we can determine the value of R1, which is 2 kilo ohm. Now, this is a series configuration. Therefore, the same current will flow through all the elements in this circuit. That is, the current flowing through the source Is, the source current, is basically equal to the current flowing through resistor R3, which is I3. Now, we know the total resistance and we know the source current. Thus, using Ohm's law, we can determine E, which is equal to ISRT or I3RT and is equal to 72 volts. Power distribution in a series circuit. In any electrical system, the power applied will equal the power dissipated or absorbed. The input power is always supplied by the source and the power is dissipated or absorbed through the loads. In this case, we have one source which will supply the input power, and over here we have three loads R1, R2 and R3. Therefore, the input power will be equal to the summation of the power dissipated or absorbed through R1, R2 and R3. In equation form, that is equal to PE equals PR1 plus PR2 plus PR3. Example. For this given circuit, at first we have to determine the total resistance RT. As we can see that R1, R2 and R3 are connected in series. Therefore, RT equals R1 plus R2 plus R3, which is 6 kilo ohm. B. Calculate the current Is. That is, we have to determine the source current Is, which is this one. We know the source voltage, that is 36 volts. We know that the total resistance is 6 kilo ohm. Therefore, using Ohm's law, we can determine Is, which is equal to E by RT. In this case, 6 milliampere. C. Determine the voltage across each resistor. We know that in series configuration, the same current will flow through all the elements. Thus, Is is the current that will flow through R1, R2 and R3. We know the resistances of R1, R2 and R3 respectively. Thus, using Ohm's law, we can determine V1, the potential drop across R1, V2, the potential drop across R2 and V3, the potential drop across R3. which will be 6 volt, 18 volts and 12 volts. Next, we have to find the power supplied by the battery. Well, we know the voltage across the battery, which is 36 volts, and we know the current flowing through the battery, which is 6 milliampere. Therefore, we can calculate the power using the formula E times I, which in this case is 216 milliwatt. Then we have to find the power dissipated by each resistor. Well, for each of the resistors, we know the resistances, we know potential drop across each of the resistors, and we also know the current flowing through the resistor. So, we can use any of the formulas for power. That is, we can use power, we can calculate power using the formula P equals VI, or P equals V square by R, or P equals I square R. Over here, all the three methods are shown. So, you can choose any one of the method or you can use all three of them. P1, P2 and P3 are determined to be 36 milliwatt, 108 milliwatt and 72 milliwatt. The last question says that we have to comment on whether the total power supplied equals the total power dissipated. Using the formula, we can prove that the total power supplied equals the total power dissipated. In the previous examples, we have applied Ohm's law to solve problems. Now, we will study another law known as the Kirchhoff's voltage law or KVL. According to KVL, the algebraic sum of the potential rises and drops around a closed path or closed loop is 0. Let me explain this statement using the given figure. So, in order to form a closed path or closed loop, suppose if we start from here, then we have to come back to this point to create a closed loop or closed path. Now, consider node D. Node D is grounded, which means it is at zero potential. Node C and node D are basically connected using a wire. There is no load in between these 2 points. So basically they are at the same potential, which is 0 volt. Node A is at E volts because the source is supplying E volts over here. So the voltage at node A is equal to E volts. As current flows through resistor R1, there will be a potential drop V1 across it. So, if there is a potential drop of V1 across R1, at node B, we will get a voltage which is equal to E minus V1. Now, as the current flows through R2, there will be a potential drop of V2 across R2. So, at point C, we will get E1 minus V1 minus V2 equal to 0. Now, if you remember, previously I have mentioned that when we move from lower potential to higher potential, that particular voltage is represented by a positive sign. And when we move from higher potential to lower potential, that particular voltage is represented with a negative sign. Thus, writing out the sequences with the voltages and the signs results in this following equation. That is, E minus V1 minus V2 equal to 0. The result is particularly interesting because it tells us that the applied voltage of a series DC circuit will equal the sum of the voltage drops of the circuit.